Today's keeper is keeper 2.1, limits from graphs and graphs from limits. All right, so the very first thing we want to talk about is the definition of a limit. Basically, a limit says as x gets close to some number, f of x gets close to some limit. You've discussed this or you've seen it before in your algebra classes when you discussed in behavior. If you remember with in behavior, you would say something like as x goes to infinity, f of x goes to 5. Or as x goes to infinity, f of x goes to infinity. It's the same concept, except we're not just looking at infinities. We can look at any number, any x value, and can determine what the limit is for that x value. In calculus, we write it in a more formal way than you've probably seen it written before. So if you look at the very bottom, we write it as the limit as x goes to a, f of x equals L. This is your formal definition of a limit. All right, so let's try to break down the meaning of some of these. So this first one, written in our calculus form, it says limit x approaches to f of x equals 5. Now, if I was to formally say it or formally discuss what this is talking about, I'd basically say f of x is approaching some number 5 as x approaches 2 from the left and the right. Now, I'm put that in parentheses, but I'm being very specific. If I say that f of x is approaching 5 as x approaches 2, I need to make sure that everyone understands I'm approaching 2 from both sides. It's not from just one side or from the other side. I'm approaching that number 2 from both sides. And I'll show you in a second what it looks like to approach from the left versus the right. All right, so this one looks a little different. We have the limit as x approaches -2 with a little plus sign, f of x equals 3. This is basically, again, interpreted as f of x approaches 3 as x approaches -2 from the right. Now, notice specifically this time I'm talking about from the right, and I'm saying from the right because of this little plus sign up here. Anytime you see that little plus sign, that's indicating that we're approaching from the right. All right, this one says the limit as x approaches infinity, f of x equals 0. So again, interpreting that, I would say f of x approaches 0 as x approaches positive infinity. And again, I know it's positive infinity because there's no sign in front of the infinity. It's just infinity, there's no negative, so I know it was positive infinity. All right, and the last one like this, we have the limit as x approaches 1 with a little minus sign, f of x equals infinity. Interpreted as f of x approaches positive infinity as x approaches 1. And again, from the left, and that left, we knew it was left because of the minus sign up here. All right, so here's an example. It says, let's find the following limits, and this time we're trying to find it from a table. So the first thing I want you guys to note on this table is that we have these x values across the top of the table. And so these x values are really important because they're increasing by a very, very small increment. So as I go across this table, I'm increasing by a very, very little bit each and every time. So if I want to discuss the limit, I can do that because I'm looking at numbers that are only increasing by small increments. All right, so the first example says, find the limit as x approaches 9 of f of x. So what I'm going to do is I'm going to find 9 on my table, which is right here. All right. So once I have 9, I want to find the limit of f of x. So this very first problem is only discussing f of x. So on the left-hand side of my table, I'm going to focus on the one that says f of x. All right. So as I'm approaching 9, I need to figure out what this limit is. So on the left-hand side, so going towards 9 from the left, it appears that my number is getting bigger and bigger and bigger, but only by a little bit at a time, and it's getting closer and closer to the number 6. Now, as I approach it from the right, so I'm going this way now, my number is getting closer and closer to 6. Therefore, my limit as x approaches 9, f of x equals 6. Now, just to make sure I'm very, very clear, I didn't care about this number in the middle. This number 6 in the middle is irrelevant to me. That is what f of 9 is. They're not asking me what f of 9 is. They're asking me what the limit is. And it just so happened in this case to be the same number. It does not always have to be the same number. And also I want to point out that make sure whatever the limit is approaching from the left also equals the limit from the right. All right, the next example says the limit as x approaches 9 of g of x. So again, I'm going to look on the left-hand side of my table. I'm going to find g of x, and I'm only going to focus on that row. So again, approaching 9 from the left, I see that this number is approaching, it looks like 16. All right, now if I look on the other side, I want to approach it from the right. This number also looks like it's approaching 16. Therefore, the limit as x approaches 9 of g of x must be 16. Again, I want to point out this undefined. The fact that it's undefined does not matter to me. I just need to make sure that the limit on the left, or the numbers on the left, are getting close to the number, and the numbers on the right are getting close to that same exact number. All right, the last one, the limit as x approaches 9 of h of x. Again, I want to find h of x on my table, which is the last row. Only focus on that. And I want the limit as x approaches 9 from the left. So I'm going this way. And I see that number is approaching 6. And then when I go from the right, so I'm going this way, it is very clear that that number is approaching 16. So on the left, I'm approaching 6. On the right, I'm approaching 16. Those two numbers do not equal. 6 does not equal 16. Therefore, this limit does not exist. All right, again, in order for this to work, the left-hand side must equal the right-hand side. Now, just a notation reminder, or a notation thing that I need to point out. Notice here on part A, I said the limit as x approaches 9 of f of x equals 6. There was an equal sign on point A. On part B, I said it equals 16. But on part C, I did not put an equal sign. I don't use an equal sign when I'm saying it does not exist, because you can't equal something that doesn't exist. If you were to put an equal sign on the AP exam, they would dock you a point for that, because it doesn't make sense. It's contradictory. You can't equal something that's not even there to begin with. All right, moving on. All right, so now we want to look at limits from a graph. So the very first thing I need you to do is make sure that you cut this graph out and paste it in your keeper so that you have it along with your examples. All right, the first example says the limit as x approaches negative infinity g of x. So what I want to do is I want to figure out where negative infinity is on my graph. Negative infinity is the furthest left that you can possibly imagine, not necessarily what you can see on the graph, but the furthest left that it actually goes. So I have it circled, and you want to kind of imagine what it's doing as it goes further and further left. So thinking about this, I see this graph is going up, and then all of a sudden it starts to level off to y equals 2. So that means my limit as x approaches negative infinity, g of x would be 2. All right, the next problem says find the limit as x approaches 9 from the left. So I want to identify where 9 is on my graph, and I only want to look at the left-hand side of 9. So again, for me, I'm going to start somewhere on the left, and I'm just going to drag my pen and see where it stops on that left-hand side. And so when I do that, I notice that this thing stops at about y equals negative 2. So if you look across, you'd see it equals negative 2. Now, if I do the same thing, but I focus only on the right-hand side of 9, so I start on the right, and I drag my pen down towards the graph. On that right-hand side, it stops a little bit further down, and it looks like that is negative 5. So the limit as x approaches 9 from the right, g of x is negative 5. Now the last question says, what is the limit as x approaches 9 straight up? Not from the left, not from the right, just what is the limit? Now if you remember your definition of what we talked about a couple of slides ago, in order for this limit to exist, the limit from the left and the limit from the right has to be the same thing. So not only can I see from the graph that this left-hand side is way shorter than the right-hand side, so this piece over here is way shorter than this piece, but I can also tell from my answers from the previous two questions. From the limit as x approaches 9 from the left, we got negative 2. But on the limit as x approaches 9 from the right, we got negative 5. Those two answers are not the same. Therefore, the limit as x approaches 9, g of x, does not exist. Note that I did not put an equal sign. Remember, we cannot equal something that doesn't exist. All right, next example. We have the limit as x approaches 0, and they didn't put a plus or a minus sign, so we're just looking on the left and the right of g of x. Very first thing, find 0 on the graph. And then look on the left-hand side of 0 and see if it equals the right-hand side of 0. So on the left-hand side, I'm approaching my graph, and it looks like I'm going down to, I don't know, 0.5, 0.75, something like that. And then if I do the right-hand side of the graph, that's going towards that same exact number. And so we just say what that number is. Since the left and the right are going to the same number, we can say that the limit is approximately 0.75. Or if you see it as 0.5, maybe say it equals 0.5. You don't have to be exact or precise or anything like that when it's not crossing at an exact number. All right, next we have the limit as x approaches 5 from the left. So I find 5, and they kind of drew it out for us. They put a vertical line at 5 so that we can see it. And I want the left-hand side of 5. Now, the left-hand side of 5 looks really, really crazy in this graph, because basically this graph is like bouncing up and down, then it starts bouncing up and down, and it's getting real tight and tight and tight, and it's coming together. But it's oscillating, and it's oscillating at the same exact height. So as I get closer to 5, it's bouncing up and down between these two values. It looks like between -1 and 1, it's bouncing up and down, up and down, up and down. That means that I can't specify what that limit is, because I don't know if it's -1 or 1 or somewhere in between -1 and 1. So the left-hand side of 5, because it's oscillating and it's oscillating at the same height, that limit is going to be does not exist. Now, if I look at the right-hand side of 5, so I pick some point on the right and I go towards 5, I notice that this line is going down and down and down and down. If I was to continue like off the graph, it's going down and down, all the way down to negative infinity. So the limit on the right-hand side of 5 is negative infinity. All right, the next one says the limit as x approaches 3. And again, we don't have a right or a left, so we need to account for both sides of that. On the left-hand side of 3, I'm approaching 1. And on the right-hand side of 3, I'm approaching 1. Even though it doesn't exist up here at 1, the limit is still approaching 1 on the left and the right. So I would say that limit is 1. All right, moving forward. Next one we have the limit as x approaches infinity of g of x. So again, I identify where infinity is. I have some crazy oscillation going on again, right? But the difference in this oscillation versus the last oscillation is that this oscillation is decreasing in height. In other words, it's getting smaller and smaller. And not only is it getting smaller and smaller, it's getting smaller and smaller to the x-axis, which is y equals 0. So the limit as x approaches infinity of g of x is 0. Again, this one works because the height of the oscillation was decreasing. Next, we have the limit as x approaches -2 from the left of g of x. So on the left of -2, so this vertical line here is -2. On the left, I'm starting and I go down towards -2. That stops at -2. Now on the right-hand side of -2, so the limit as x approaches -2 from the right, that's going up to infinity. And so our limit is infinity. Well, what's the limit as x approaches -2? Period. So again, when it doesn't have a left or a right-hand symbol, you have to consider both sides and they have to be equal. Well, from the left, we said it was -2. On the right, we said it was infinity. So that means those two numbers are not the same. This limit does not exist. All right, now just like a quick review, this is like old school, but I want to make sure we understand the difference between limits versus like your regular function notation. So the very first one says g of 3. So the first thing I'm going to do is I'm going to identify 3 on my graph. 3 is right here. All right, now g of 3 is wherever 3 exists, right? It's not about the limit. I don't care what the limit is. I want to know what it actually is at 3. Well, it can't be 1 because this is the open circle up here. So I can't use 1. But if I notice, I do have a closed circle down here. And so g of 3 is -2. All right, if I do the same thing for g of -2, I identify -2, which is this line right here. And I want to figure out what value is it? Where does it touch -2? Well, this side, the right-hand side, goes up forever and it never touches -2. And then the left-hand side is coming down to an open circle. And so because that circle is open, we're going to say g of -2 doesn't exist. All right, next we have g of 5. So again, I want to identify where 5 is on my graph, which is this line right here. And I noticed that on the right-hand side, it's going down to -infinity. And then on the left-hand side, we had that oscillation going on. So it never actually touched it. It was just bouncing back and forth, getting really, really close to it. And so again, because it never touches 5, we say that this does not exist. All right, the very last one, we have g of 9. So again, I want to identify where 9 is, somewhere like right here. And I want to figure out where it actually touches 9. I don't care about the limit, I want to know where it touches it. Well, right down here, we have an open circle, but up here, we have a closed circle. So I would go with the closed circle because that's where it's actually defined. And that closed circle happens at -2. All right, this question asks us to look at the graph and determine which values of x does the graph exist, does the limit of the graph exist. I find it to be a little bit easier to look to find out where it doesn't exist. And then once I know where it doesn't exist, then I can say where it exists. So what I look for is I look for like holes in my graph. I look for asymptotes. I look for jumps. Anything that looks like a little funky, any oscillation, anything that looks a little weird. I identify those areas, determine if the limit exists, and if it doesn't, then it doesn't. And if it does, then I know it exists there. So the first thing I look at on this graph is at -4. At -4, I notice there's like this little jump going on right there. That jump makes me very, very uncomfortable because I need to check to make sure that the limit from the left and the limit from the right equal. So again, when I look at this little jump, I'm like, what's the limit from the left? Well, the limit from the left, as I approach from the left, is going up to 6. And the limit from the right, as I approach -4, is going up to 4. Well, 6 doesn't equal 4, so therefore the limit there does not exist. Now at 2, I see I have a hole in my graph. And again, that makes me a little bit uncomfortable, a little uneasy, so I check my limits. The limit as x approaches 2 from the left is going to 2. And the limit as x approaches 2 from the right is also going to 2. So because the left equals the right, boom, my limit exists. The only place in this graph that I can see from what they gave us that has an issue is right here at -4. All right, so if they ask where does it exist, well, it exists everywhere but -4. So using interval notation, I say -infinity to -4, union -4 to infinity. Doing the same thing for this graph, again, I want to identify any places that make me feel a little uncomfortable. Well, the first thing I notice is I have an asymptote here at -5. And so again, I want to check my limits. So the limit from the left of -5 is going up to infinity. On the right-hand side of -5, the graph is going up to infinity. The left-hand side equals the right-hand side. -5 is not a problem. Now, if I look right here at this hole that's happening at -2, I want to check my limits there. So the limit from the left of -2 is going down to -1. The limit from the right of -2 is going up to 1. Because those two numbers are the same, both of them are 1, I don't have a problem here at -2 either. The limit exists at -2. The last place that I find a problem is over here at 3. And I want to check my limit. So on the left-hand side of 3, I'm going up to 3. And then on the right-hand side of 3, it's approaching 4. 3 does not equal 4. Therefore, the limit does not exist at 3. That means from what I can see, from what's drawn, from what they gave me, the limit exists every single spot, everywhere, except for at 3. So my answer would be -infinity to 3, union 3 to infinity. Okay, our last concept for today is graphing from limits. So if I give you a set of limits, can you create the graph from those limits? All right, so in this example, I'm giving you 3 limit statements, and I'm also giving you like an f of x equals y statement. If it was me, I generally typically start with the f of whatever statement because I know for sure what that is. So again, for me, I'm going to go ahead and start with the f of 1 equals 2 because I know for sure that that's going to be the point 1, 2. So I plot that point. All right, after that, I just start working my limit statements. The very first statement says the limit as x approaches infinity of f of x equals 2. What that tells me is that I must have something going on as I go out far right. The graph has to be leveling off to 2, which means it's probably a horizontal asymptote. So I put a little asymptote at 2, and I want to draw like a little curve or a little piece of a curve that's curving off at 2. Now, I don't know if that curve is above or below, so I'm just going to put 2 little marks to indicate that's where it's going, and I'll choose which one later depending on like what the actual graph looks like and how the graph actually moves. All right, so then moving on, I have the limit as x approaches 1 of f of x equals negative 2. And so that means since it says x approaches 1 and it didn't give me it from the right or the left, I know that it is from both the right and the left that it equals negative 2. So at 1, I'm going to go down to negative 2. I'm using an open circle because I already closed the circle from my initial state, my initial piece that I plotted, f of 1 equals 2. And I know on the left and on the right of 1, that is going to be at negative 2. So I put 2 little arrows there as well. Again, remember the little blue arrows that you're seeing, that's just me like getting a quick sketch of the graph. And then I'll curve it out and make it look better when I'm done. All right, the very last limit statement says the limit as x approaches negative infinity, f of x equals 2. So that means as I go far left on this graph, I'm leveling off to 2, indicating that again, I must have some type of horizontal asymptote at 2. Now again, I don't know if that's going to approach from the top or on the bottom, so I just put a little arrow and I'll choose in the end. Once you have all your little sketch pieces, all your little arrows in, your closed circles, your open circles, what you want to do is connect the arrows. So basically, what you want to do is connect what flows well. So when I'm looking at this side, this left-hand side of the graph, I want to connect it to the next closest arrow. So I'm like going left or right. Now, I don't want to choose this top arrow because if I choose the top arrow, I'm going to have to cross the asymptote, and I don't want to do that. So instead, I'm going to choose the bottom arrow, and I'm going to curve and go straight into that next arrow. So that kind of makes sense. And again, you can draw it however you want to draw it. There's no right or wrong way. It just needs to connect nicely. All right, so then again, still working from right to left, or sorry, left to right. I'm starting right here, and I'm going to the next closest arrow, which would be one of these on the far right. Now, I don't know which ones to use, but again, I want to try to avoid crossing my asymptote if I can. Not that I can if I want to, but then I have to bounce back down towards it. So I'm just going to make it smooth and connect from this bottom arrow to this arrow right here, and I get some type of curve that looks like this. All right, the last example for the day, we're going to do the same exact thing. So we have the limit as x approaches infinity, g of x equals 0. That means I must have a horizontal asymptote at 0. And we have the limit as x approaches negative 2 from the right is infinity. So at negative 2, I'm going to put an asymptote there. And on the right-hand side, I'm going to go up to infinity. Then on the left-hand side, it says the limit. So the limit as x approaches negative 2 from the left, that also goes up to infinity. So I'm putting an arrow going up there. The last piece of this says the limit as x approaches negative infinity, g of x equals 0. That means on the left-hand side of the graph, it's leveling off to 0. And just like before, I didn't know to use the top or the bottom, so I put an arrow on both. All right, now that I got all my little sketch marks in there, I'm going to connect my sketch marks. And again, I'm just going to try to make it as smooth and pretty as possible without, violating any mathematical laws. So for this left-hand side, again, I'm working left to right. So on this left-hand side, I'm going to choose this top arrow because the bottom arrow would make me have to cross the asymptote. So I'm going to choose the top arrow, and I'm going to connect it to the next closest arrow, which would be that one. All right, once I connect those, I get a nice pretty curve. And then continuing left to right, I'm going to start with this next arrow, and I'm going to connect this to the closest arrow that's like reasonable without crossing any crazy asymptotes. So that would also be the top one over here. And I'm going to connect those, and I get my curve. And it's always good form once you get your curve to go back and, actually check your own statements, check to make sure it actually matches your drawing, just to make sure that your graph is accurate.